Hello, welcome back to the liquid chromatography lectures. In this video, we are going to look into the reverse phase chromatography. And as told before, reverse phase chromatography is the most commonly used type of liquid chromatography. And therefore, it's very, very important to understand what is going on. So let us dig directly into the mechanism of reverse phase chromatography. The heart, of course, again, is in the column and in the interactions that are determining the retention in the reverse phase chromatography. And the stationary phase in reverse phase chromatography is usually based on silica particles. So silica particles are these silica oxygen frameworks. Usually the particles are having silanal groups on top, but in reverse phase chromatography, we do not use silica particles directly, but we modify these particles. And we modify these particles by chemically reacting some inert non-polar groups to the surface of the silica particles. So most commonly, we use something which is called C18 reverse phase chromatography. So that means that the silica particles have been reacted so that the silanal groups have been converted into alkyl chains that have 18 carbons here. So these particles are all smoothly covered with the C18 groups. And it doesn't necessarily have to be C18, but C18 is by far the most common one. Also C8, so 8 carbon long alkane chains are also common, but C18s are most common. Additionally, also other types are possible, for example, ones which contain aromatic groups as well, which are specifically then designed to separate and retain aromatic compounds. But the most common ones are the C18 ones. And these surface of the stationary phase particles now is non-polar. So the polarity of the stationary phase is very, very low. And this we have to keep in mind. On the contrary, the mobile phase in the reverse phase chromatography is very, very polar. The starting point of the mobile phase is a pure water. And in pure water, we have extensive network of hydrogen bonds between the water molecules. So we see that each of the water molecules almost is bonding with a hydrogen bond with the next water molecule in this mobile phase. And this means that the mobile phase molecule interactions are very, very strong. So mobile phase interaction is very strong. So what would happen if we would now add analytes or our sample to this mobile phase? Of course, partially the analytes, if they have some polar groups, would also start interacting with the mobile phase. So they could also interact, and analyte mobile phase interactions would become important. However, if there are some more hydrophobic moieties in the molecules, or they are not really very polar, then it would be very, very hard for these analyte molecules to compete with the extensive hydrogen bonding network of the water. So they would be very strongly pressed to the stationary phase. And this is actually a very important concept in reverse phase chromatography, that analytes do not necessarily interact with the stationary phase because they themselves have affinity towards stationary phase, but rather they are pushed to the stationary phase due to the fact that mobile phase interactions are stronger than the analyte mobile phase interactions, and the analyte is therefore partitioning to the stationary phase. Um, Also, I've already mentioned word partitioning, and this comes from the fact that mobile phase, of course, is a liquid, and this extensive layer of C18 groups that we have in the reverse phase chromatography, we are also viewing this very similar to a liquid phase. So this is acting like a liquid-liquid, like an analyte partitioning between two liquids. One of these liquids, the mobile phase, is very polar, and the stationary phase, or actually the surface of the particles of the silica gel particles, the C18 groups, they acting as another liquid, a very non-polar liquid. So the question now is the compound polar enough to actually go to the mobile phase, or is it completely pushed to the stationary phase? However, a lot of compounds would not be polar enough to actually be carried through the column because they would just not compete with the extensive network of the water molecules, of the hydrogen bonds of the water molecules in the mobile phase. So we need to do something to also make the mobile phase a bit less interacting with itself. So to make the mobile phase interactions weaker and to allow the analyte to actually move through the column. And to achieve this, we don't use pure water in reverse phase chromatography, but we mix it either with acetonitrile or with methanol. And with this, we break the water hydrogen bonded network, and we allow the analyte to also go into the mobile phase and move further in the columns. So it's very important to add this organic modifier, organic solvent to our mobile phase to actually elute the compound. If we would use only pure water, most of our compounds would be all of the time retained in the stationary phase and would not dilute from the columns at all. So to make them elute, we need to add organic modifier. So important part here is the partitioning between the stationary phase and between the mobile phase, and the important interactions in reverse phase chromatography are mobile phase interactions and analyte mobile phase interactions. Analyte stationary phase interactions can be important in cases where we have some specific stationary phases. For example, when we have some aromatic groups also on our stationary phases. However, if we have C8 or C18 stationary phases, then these interactions are very minimal compared to an analyte mobile phase and mobile phase interactions. Mobile phase stationary phase interaction is also not so important in reverse phase chromatography because the mobile phase is largely polar, the stationary phase is non-polar, and they are just not really very much interacting with each other. Now, it would be important to also understand this on the generic polarity scheme of the analyte and eluent. The analytes that we are determining or that we can separate with reverse phase chromatography are not too polar, so they are not ionic compounds. We can't separate chloride ions from fluoride ions, for example. And also two polar compounds can't be separated. For example, we can't separate polar aromatic hydrocarbons from each other. This is just not possible. The eluent is also medium polarity. This means that we don't use pure water, which would be the most polar one, because then our compounds would just not elute from the column. And it's also not the most non-polar one because our analytes simply are of medium polarity, and our analytes would need to dissolve in it. And also two non-polar eluents would have too high eluting power. So this means that the compounds would come out from the columns too fast. But our stationary phase is very non-polar, mostly. There are some exceptions which are specific techniques, but then they also usually have a separate names. The name they are rather not classified under the reverse phase chromatography. So analytes which are too nonpolar, so for example, these polyaromatic hydrocarbons, they bond so strongly with the stationary phase that they do not dilute. So we can't separate them with reverse phase chromatography. Analytes which are very polar, so for example, anions or cations, inorganic especially, they are they are interacting with the mobile phase so strongly that they are not pushed to the stationary phase at all, and they aren't retained. So this means that they all come out from the column at the dead time together with the mobile phase front, and they would just not be separated therefore at all either. Eluent. If the eluent would be very polar, then nothing would elute. So for example, when we had just pure water molecules, their extensive hydrogen bonded network was so strong that all of the analytes were pushed to the stationary phase and nothing would come out from the column. And if the eluent is too nonpolar, then everything elutes too fast. So this would be, for example, if we would try to use hexane in reverse phase chromatography. So the main idea here is the partitioning between the stationary phase and the mobile phase, and you might assume that the compound properties play here a major role. Generally said, the compounds which have higher log P values, so which are less polar, are eluting later. And this is also a kind of a good way to determine if a compound would be eluting earlier or later than another compound. A good way is just to look at the log P values of the compound and say, okay, the compound which has a higher log P is eluting later. Now, some compounds also can undergo dissociation. For example, benzoic acid here can be present in the mobile phase either as an acidic benzoic acid, a neutral benzoic acid, or as a benzoate anion. And now the question is, would that matter? Does that somehow influence our chromatographic separation? And the truth is that yes, it does, because the benzoic acid and the benzoate anion are interacting with the mobile phase with a different strength. The anionic form is, of course, interacting stronger with the mobile phase, with the polar mobile phase, while the benzoic acid is somewhat weaker in interacting with the mobile phase. So we could think, what happens then when we change the pH of the mobile phase that is carrying through our analytes, our samples, through the column? So let's start with a case where we have a low pH mobile phase. So we have buffered our mobile phase with something acidic. For example, a common thing to do in HPLC mass spectrometry is to add formic acid to the water phase. So make it very acidic by, for example, adding 0.1% of formic acid. And we could have with this a retention pH of 2.7. Benzoic acid has a pKa of 4.2. And I would now like you to think for a few seconds, in what form is benzoic acid predominantly at pH 2.7? Is it rather the neutral form or is it the anionic form? Okay, maybe you have thought about that. If you haven't, take the pen and paper and do the math based on what is the definition of pKa, what is the pH, and calculate out in what form the benzoic acid is predominantly at this pH. And hopefully you will reach the conclusion that the benzoic acid is predominantly in the neutral acid form. So now what happens when we increase the pH? So let's, for example, say that we increase the pH of the water phase to pH 5. pH 5 is now close to the, or actually slightly above the pKa, and close to the pKa plus minus 1 pH unit. We say that both the contribution of both the neutral form and the anionic form is significant. However, here we can say that the anionic form is actually a bit higher in concentration because the pH is higher than the pKa value. The effect on the chromatogram is that now the anionic form that is dominating, or which concentration, relative concentration in the solution has increased relative compared to the pH 2.7 mobile phase, we see that it is interacting more stronger with the mobile phase, and therefore it is also eluting faster from the column. So now we see a much shorter retention time. And when we increase the pH of the mobile phase even further to pH 8, for example, then we have almost only the anionic form, and we see that the retention time of the benzoic acid peak has decreased even more. So it is now eluting really, really early. So this means that pH is a very important factor in the elution of compounds which can ionize in the mobile phase. And this actually gives us multiple considerations here. Firstly, it means that we also always need to buffer our mobile phases in reverse phase chromatography to be sure that our compounds would always elute from the column at the same retention time, and this would not vary depending on the pH of the sample or even random fluctuations in the conditions. So the pH would need to be very, very stable in the mobile phase to always get the same retention time. The second thing is that when we try to separate the compounds in liquid chromatography, and this is the key process that we need to do, we need we can a lot achieve by changing the pH of the mobile phase. So optimizing the pH of the mobile phase is one very crucial part when we optimize the separation of the compounds in reverse phase chromatography, especially if our compounds have ionizable groups. If our compounds do not have ionizable groups, or the pKa's of all of our compounds are very similar, then this is not so important. But if they do and their pKa's are different or slightly different, then adjusting the pH is one possibility to achieve separation of our compounds. Another very important factor in the chromatographic separation with the reverse phase chromatography is choosing the mode of elution. The traditional way is an isocratic elution. This means that during the whole chromatographic run, the mobile phase composition is the same. So for example, we mix the water phase with acetonitrile at a 50-50 ratio, something that we can denote like this. And we use this all throughout the chromatographic run. Usually we get some kind of a chromatogram like this when we have 3 compounds, let's say. And we see here 2 problems. Firstly, the peaks are fairly widely separated, and it takes kind of lot of time to get all of these compounds out from the column. And we see an even maybe larger problem, and this is that the late eluting compounds have very broad peaks. So the peak heights are much smaller, but they are much broader compared to the first peak, which is nice sharp peak. And one possibility to overcome these drawbacks, so both to make the analysis faster and to keep the peaks relatively shape independent of being late or early elutor, is to use gradient dilution. Gradient dilution is a program where we increase the organic modifier percentage with the time. So usually we start with a few percentage of organic modifier, like for example, 5%. We increase it to 100 or sometimes 95%, and we hold it for a few percent and then return it back. Why do we start with a few percentage of organic modifier is that if we would use pure water phase, then the C18 change that are on the stationary phase may get a bit damaged. So we know that their structure can change a bit if we expose the column for a longer period of time with 100% water. And another thing is that actually 100% water doesn't elute almost anything from the column, so it's not a very useful percentage to start with. So usually we start with a few percentage of acetonitrile or methanol. Then we increase, so in this time, the eluting power of the mobile phase is increasing. So we often talk about eluting power in HPLC, and the organic modifier is always the component that has higher eluting power, and water phase has lower eluting power. So we increase the eluting power of the whole mobile phase by increasing the percentage of the component organic modifier which has higher eluting power. Usually we reach in the end some kind of a plateau, and we keep our organic modifier content there stable for a few minutes. And this is to flush out from the column all compounds that can have very low that can be late eluting, either analytes or also matrix components, because not everything that we are injecting to our column is actually of interest. Everything is not our analyte. So we also have to flush the column from the matrix components that we are not interested in. And lastly, we return then to the original composition. Important to mention that often this plateau, the highest percentage of organic modifier can be 100%, but if we are dealing with samples that could have proteins or other compounds that might precipitate at 100% organic modifier concentrations, then we might stop at 90 or 95%. So for biological samples like blood extracts or urine extracts, we mostly actually stop at 95% of acetonitrile. So let's view what kind of effect has the gradient dilution on the separation of the compounds. So this was our ISOCRATIC run. This is our gradient program. And what we see in the gradient dilution is that as the gradient is increasing the percentage of the acetonitrile, our peaks elute nicely. So this time of these peaks coming out from the columns is here becoming much shorter, because we speed up the elution of each of these peaks by constantly increasing the elution power of our mobile phase. And also we see now 3 sharp peaks of almost equal width. So this means that we do not anymore lose efficiency with longer retention times. So gradient dilution has provided us here with 2 very crucial benefits. Firstly, we get our compounds out from the column faster, but we also get the peaks much narrower and peaks higher, especially for the late eluting compounds. And this is very important from the signal to noise perspective. So very wide peaks, even if their peak areas are exactly the same. For example, here, the peak areas for the isocratic run and the gradient run are the same for all of these three peaks. And only for the gradient dilution, we see a very nice sharp peak. And this, of course, is much simpler to detect. So the signal to noise ratio is much higher with the gradient dilution, usually for the late eluting peaks. In isocratic elution, it can very fast become questionable. Oh, is that actually a peak, or is that just a slight blip on the baseline of the chromatogram? So gradient dilution also usually provides us better signal to noise ratios. So this was a short introduction to the reverse phase chromatography, and in the next videos we are going to shortly look into the normal phase chromatography as well as helichromatography. See you then.